All right. So this is about where we left off last time, right? We built the student class, and then we're building the course class. The big things were, well, first of all, the student class was just, it's not intended to be particularly anything special. It's just what we want to store in the course object for the sake of demonstrating a data structure. But we did see with the student class, it was a little funny because our EQ was a little different than before. Before, equality was check all the attributes. Here, I decided let's only check if the student numbers are the same. With repr, it's a little different than the convention we followed before where it was class name parentheses attributes. Here, it's just last name, comma, first name, tab, student number. And the reason for that is because of what I have in mind for the design of my program, this is what I want. The course, we've got the constructor. The big thing here was, one, not all attributes, like the parameters that your constructor gets and the attributes, they're not necessarily related, right? I have the course name as a parameter here, and that's one of the attributes. But another attribute, that students, has nothing to do with the parameter list. Nothing at all. It just, we need an attribute that's going to be a list to hold on to the student objects, but there's no parameterized value I care about for the setup of this. So I just create the empty list there. And we also saw that underscore before the name of the attribute. So it's underscore students. And that underscore has a special meaning, pardon me, and the meaning is no one's supposed to touch this. It's not, this attribute is not meant to be accessed outside of this class. It could be accessed from within the class, but not outside the class. We also saw a size method there. It just returns the length of the attribute, the students list, which is the attribute underscore students. And we also have add, which basically just appends to the list. That's it. That's all we've got. We have a find. Find is just a linear search that returns the index of a given thing, but it starts with an underscore. So that is a method now that is not supposed to be accessed outside of this class. It can be accessed from within, but not outside of the class because it doesn't really have a purpose outside the class. But it exists inside the class to help make contains easier. Because for contains, I just want to write a method that tells me whether or not something exists inside this collection. So all I need to do is do a linear search. And if the result of that linear search, if the result of calling find is anything but -1, it's there. If it returns -1, which is of course the constant not found, which is just -1. If you don't believe me, there you go. If contains calls find and find returns -1, that means the thing wasn't there, therefore I return false, which would be the result of not found not equals self.find of the student. And then finally we have remove. Remove first checks, okay, if you want to remove the student from the collection, does it exist inside the collection? If it doesn't exist, what do we do? Well, I don't know what you want to do, but this is a good use of an exception. If you try to remove something from this collection that doesn't exist, does that mean something went wrong? Should I just ignore it? Should the program crash? I don't know. But what I do know is I can give you an exception, and then the person using my code, if they ever see that exception, they can decide what they want to do. So that's what we're doing there. So if it's not there, if the thing I want to remove isn't contained, and we call contains, it's just this method here. We say raise that value error. Otherwise, just pop the thing at the index of whatever find gives me. So pop is a method on a list where if you give it an index, it removes the value at that index and everything moves down, or I guess down, to fill that gap. That's all. So if I had the list like A, B, C, D, and I said pop index 1, I would get a list that's A, C, D. Eliminated the thing at index 1. And here are some quick checks here for the, yeah, okay, cool. Any questions so far? This was just a review of what we did last time. All right. Now, we stopped here last time because I wanted to make sure we had a chance to talk about it. Well, don't know what's going on there. Here is my repr. And what on earth is this doing? This right here is a common pattern you will find with collections reprs. Take a moment, look at this code, and try to make sense of what it's doing. Oh, I'm going to give you a minute to look at this code and think about it. Nothing in here is new, really. I'm actually going to modify it a little bit. There. There. I've modified it for fun. Let's talk about it. So the first line there, line 31 is, okay, create a string that's just going to be the course name, which is an attribute of the object, of the instance. So it's going to be the course name with a new line at the end. So it's just the string course name, new line. But then we're looping over each student in the attribute students, which is just a list. So for each student in the list, S plus equals. What happens if you call plus equals on a string? It concatenate. It's the same thing as writing S equals S plus on a string. It's basically taking the string, concatenating with another string, and storing it back into S. This is string building. And what do we add to it? Well, we add after that new line, the first student, we add a tab. And then we take the string representation of a student followed by a new line. And then we repeat until we're done. And at the very end, we return S. Now remember, just a big thing I want to emphasize here, your reprs do not print anything. They return a string. They don't print anything. So, let's see what happens when I run this. Now you'll notice the formatting's off, just a consequence of how long Niles McDonald is and how the tab worked. But that's how I wanted my repr to work for a course object. First line is the course name. New line. Tab over, first student. We take the string representation of the first student. Where did we define the string representation of a student? In the student class. So if you're wondering, how did it know to give me the string representation of a student? Well, because we defined what it means to give you the string representation of a student. That's why. If we eliminated this and rerun it, and rerun this, we'll just get the default string representation of a student, which is a heck of a lot less helpful. But that's why we wrote the repr in the way we did, because I wanted it to look like this. So I immediately know, well, Bob Smith is there, Jane Doe, Niles McDonald, and another Jane Doe apparently. They're all there. Cool. Great. That's my repr. Obviously, this is also different than the convention we've seen, where it's just class name followed by the attributes, because that wouldn't really make a lot of sense for a collection. In the same way, when you print out a list, it's kind of helpful to see the contents of the list, right? Well, that's what's going on here, but this is a specialized list. It's a list for keeping track of students. So it's defined a certain way. Any questions about this at all? So let me just make sure I'm not forgetting anything before I don't talk. Yes, okay, cool. Remember, this was all one string. We didn't like call print multiple times. No, the string had new line characters in it that we appended at the end of every time we took a string representation of the student. Questions? From the looks on half your faces, I'm expecting questions, but I'm not seeing any. Anyone want to take a wild guess why? Yes? Okay, really can't help you with that then. If you don't know what to ask, you got to try at least, so I can try to answer. If you don't know what to ask, I don't know what to answer, that's for sure. Yeah?
Where's the class, course referring to class student?
It's all based on the types. So, because here, I'm creating a student, right, that I'm immediately passing to the add method. So I'm adding a student object with the add method right here. So the things in the list are students, and the objects know what type they are. So whenever you ask an object, hey, you, give me your string representation. Because the object knows its type, because Python knows the object's type, Python knows we'll go look up that object's types, classes, repr. So the way, when I said, this means effectively by doing this, putting it into a string, call the repr for that variable there. Because the value stored, at least at the reference of where that variable gets me to, is a student, Python knows, well, it's the student's repr. In the exact same way, watch this for a moment. Look. We're going to hit pause on the course class for a moment, and here's what I'm going to do. I'm just going to create a list and put student objects in a list, okay? First, let's start with a list of integers. And I say print A. There we go. But how did Python know how to print out a list? Well, the list had a repr defined that says basically look like that. But the types of those things in the lists were integers. So how did it know how to print out an integer? Well, it just did because it was defined somewhere. Now I can mix types in here. And it's still printing out each thing, but each thing knows what its string representation is. Now in this particular example, these are all types we're used to. We probably haven't really thought of them in the context of classes before. But let's go ahead and also do this. The last element in the list is, well, the string representation of the student object. So every time the list object's repr needed to know what object to, like how to print out that object, well, it had to go look up the individual thing's class's repr in order how to do it. First, it looked at like what the integers would be, then the string, and then the Boolean, and then the student. Hell, I could do this. Now this is going to get weird, don't get me wrong. What was it called up here? My course. So I'm adding the my course object to it. But when the list gets to my course, it's going to want to call the repr for my course. Which is why we get the name of the class followed by the tabs and all the contents there. And then it's done, and then, well, the list's repr ends with the square bracket. So the way it knew was just because the objects know what their type is. So the object, when the object is told to do the repr, well, it does its respective repr. Is it the string's repr? Is it the student's repr? Is it the course's repr? Yeah. Does that answer your question? Cool. Other questions? Does anyone want to take a wild guess why defining equality on this collection might be a little difficult? Take a moment and think about it. Yeah, so that in and of itself isn't that big of a deal. I could write an equals that basically says, okay, take the first thing from this course. First check, okay, are the names the same? Okay, is the student at the beginning of the list the same as the student at the beginning of this list? And then this one and this one, right? Like I could do that. But yeah, the issue is the order. Should order matter? Does it matter if Bob Smith comes before Jane Doe? Or vice versa, in order for them to be equal? Probably not. I don't really care. In order for two courses to be the same, I just want to know if the set of students is the same between each. And I could do that. Honestly, the easiest way to do it is to take the list, convert it to a set, and then compare the sets. That's probably the easiest thing to do. But without that, it's going to get hairy, right? So writing equality for, at the end of the day, we've been writing these equals methods and they look simple, but at the end of the day, defining equality for objects is actually kind of difficult. For the simpler objects that are not too bad, but once we get to a collection, like this data structure of the course, it gets difficult to check all different possible options and whatnot. So we're just going to skip it for now. We're not going to bother defining equality. We could, but yeah, it's tricky. Other questions? All right. Okay, now to change pace a little bit. Searching and complexity. Pardon me for a moment. I keep looking at my phone because my kid had to go to the hospital. I'm just kind of keeping an eye on what's going on. So excuse that for a moment, but he's more important than you, sorry. I'm just saying. I'm going to say it. I don't know if you know that. All right, searching and complexity. So we've talked about linear searches, right? And that's a quick refresher. If I told you, here's a list of 1 billion things, can you check if such and such a thing exists inside of it? How many would you have to look at to guarantee that it's there or not? A billion things. And if I doubled the size of that input, how many things would I have to look at? Double the things, right? So the amount of work, consider the work is like, each unit of work is looking at each thing. Is this the thing I'm looking for? Is this the thing I'm looking for? Is this the thing I'm looking for? That's the unit of work. And the amount of work I need to do, the amount of work that function needs to do, if the input size doubles, the amount of work doubles. Now, when I'm talking about computational complexity like this, I want to be clear what I'm talking about. That's computational complexity, okay? We're going to talk about it from this level. We're not going to get really nitty-gritty into it. We're going to keep it high level, but it's important to know this stuff. So, when I'm talking about computational complexity, I'm not talking about how long will my program take to run. That's really not what I'm talking about. What I'm talking about is how much more work, like how does the amount of, it's not even about the amount of work your program does on any instance. It's about how much work your algorithm, your program needs to do. How the amount of work it needs to do depends on the input size and how it changes. So it's not that it needs linear amount of work, it does, but really what I'm trying to say is, as the input size changes, the amount of work I need to do changes linearly. As the input changes, if I double the input, I double the amount of work. If I quadruple the input, I quadruple the amount of work. That's really what I'm going on about. A lot of students kind of miss that and they jump into, well, how much work is that algorithm doing? That's kind of really not what we're getting at, right? Okay, so there we go. All right, so, okay, before continuing, let's hit pause on that. Let's take a moment and really reflect everything we've learned so far. Like what? We're down to like less than 2 weeks of the semester left, right? Right? So how much have we learned so far? We're not done the course yet. We're close, don't get me wrong. But how much have we actually learned? Raise your hand if you've never programmed before this course. Raise your hand if you programmed before technically, but you really didn't. Okay, there you go. So raise your hand if you have reasonably extensive programming experience before the course. 2 people went, eh. And for those, okay, put your hand up really high. I want to see, because I want to ask you a question. Really high. No, wait, no one's bold enough to say they do, actually. They did have programming experience before the course. Really high, I want to see. We have 1, 2, 3. Your hand was up. Where'd it go? So it's up now or not? Oh, the reasonable experience. Okay. And you said reasonable. Okay. Now, for those of you with programming experience, did you learn something new in this course, though? Did you? Yep. A lot or a little? Quite a bit. You? A good amount. And who else? And you? A good amount, yeah. The stuff that you probably learned wasn't really along the lines of like if and loops, right? Like you probably knew that before, right? It was probably a little bit bigger picture was the stuff that you took away from it so far. But for the most part, most of you came into this knowing shit all. But that's often a good thing. So people will complain, they'll be like, he expects you to know programming before the course. No, that's not true at all. Absolutely not. Most of the people in here had no experience. But we learn a lot. So that's the reality. It's not that I expected you to know this beforehand. No, I need you to pick this stuff up as quick as you can because there's a lot to learn. And let's take a moment and realize and get an appreciation for how much we've actually learned, okay? We started the semester with Hello World. We learned about values, we learned about variables, we learned about types. Then we learned a little bit about like input-output, right? Print and input. We learned, we used Colab. We didn't use IPython or PyCharm or Spider this semester, but we used Colab, which is a programming environment. Great, you didn't know any of that before. You know how to make functions, but you know how to use functions. We started with like print and input, right? But you know how to make your own functions to call them, which is a pretty big thing. You know about basic logic. Oh, there's a typo here. There should be a space. We learned basic logic, and we also learned some of those control structures like if statements and else. That was a big one, if and else, to make a decision in your code. Before that point, we had no way to make a decision. The code would just run start to end. Then we learned loops. We learned about for loops and while loops. We had some code we want to run multiple times. We learned how to use objects. We didn't write them at that point, but we learned how to use them because, we use lists, and lists are objects, right? I mean, everything that we're using in Python is technically an object, but that's not important right now. So we use lists. We also saw like tuples, sets, and dictionaries. Dictionaries are phenomenal. We learned how to read and write information from a file, which is a big one. We learned how to write our own classes. We learned about exceptions, too. I don't think that's on here. Yeah, we learned how to write our own objects. By this point, you could probably look at quite a bit of Python code, assuming it was well written. There's a lot of terror. If you ever look at this stage, if someone gave you a well-written chunk of Python code, you could probably look at it and figure out what it's doing. By this stage, only by having like 10/12 of the semester done, you probably could do that already. 10/12 of one semester of computer science, you could probably understand code pretty well. The stuff that you don't know yet is how do I explain this? You know all of the elementary things such that if you really wanted and you didn't learn about a tree, that we're going to learn about trees at the end of next semester, okay? But I never taught you trees. But at this point, you know enough that you could sit down and kind of work out what the hell a tree is, despite me never showing it to you. Like, you know a lot already, which is a good thing. Now, that's not to say you could look at some really poorly written Python code and be like, what the hell's going on? In the same way that I would look at really poorly written Python code and I would ask what the hell's going on too. You know about the importance of testing your code. You know how to write tests. We did the simple assert test. We learned a little bit about unit tests too. That's a big one. What else? And you really developed your skill of algorithmic thinking. You developed your skill of looking at a problem, breaking it down, and trying to solve it step by step. There's a lot that you've learned. That all happened in the last 10 weeks, which is nuts when you think about it. So if you've made it this far, congratulations. You've learned a lot. I don't know if you know this, computer science is kind of hard. So keep up the good work. Now, the last few topics of the course have been heavy on data structures. At this stage, we've already equipped ourselves with the majority of tools programmers use on a daily basis. Honestly, yeah. I don't know, I'm going to pull this number out of my ass, but let's say 80% of the stuff a programmer does on a daily basis, you know. You really do. So I want to make sure, don't ever feel remarkably insecure, oh, I'm so stupid, I don't know anything. No, you know most of it. Don't get me wrong, it's like that 80-20 rule, right? Where learning that remainder 20% actually takes a hell of a lot of work to kind of understand, and that's the rest of the degree. So yeah, we've been focusing on data structure, so it's time to take a step back and refocus to algorithms. All data structures that we write are based on the algorithms that we write. But, the algorithms are more things like a linear search is clearly a very clean, nice algorithm, for example. Where a list, that's a data structure. If we were to go open up the code of a list, you would see a bunch of algorithms. Like, how do you append to a list? Well, there's code that says how it does what it does. But when we think of the list, we think of it as a more abstract object as this like data structure. So even though there's algorithms in there, I'm talking about it at a high level. A linear search through a list, well, that's the algorithm for doing the linear search through the list. So we're going to shift focus more to algorithms right now. We're also going to take a moment to think a little bit about the amount of work an algorithm has to do. Oh, I see a new message. Hold on. Okay, nothing new. So we've talked about linear search a lot by now. Here is a very general linear search, right? Given our familiarity with the problem and the linear search algorithm, we're going to use it as a starting point to begin thinking a little deeper into algorithms, at least thinking about the work being done. So here's the algorithm. Def linear search, I've got a haystack, I've got a needle. For each element in haystack, if element is the needle, is the thing I'm looking for, if they're equal, I found it. If not, I keep going, and remember, I can only conclude that the thing isn't there if I ever look at everything and never found it. If I've looked at everything and I never found the thing I'm looking for, and there's nothing more to look at, then I conclude it's not there. The moment I find the thing, I can conclude it's there. This is where I can talk about like a best case and a worst case scenario. So first of all, let's be clear with the code, with the for loop. As soon as, if element equals needle, as soon as that condition is true, the function stops. It returns true, it's done. It doesn't need to look anymore. But it needs to run the whole loop for it ever to return false, meaning that's going to have a best and a worst case scenario. Best case scenario is I have a list of a bajillion things, and I'm looking for the letter A. And I look at the thing at the very beginning and go, oh my God, it's an A. Done. I don't need to look at the remaining bajillion minus one things. I found it. But there's also a worst case scenario, and that is the thing I'm looking for is at the very end or isn't even there at all. Meaning I need to put my finger on each of the bajillion things and actually look at it. All right? Cool? So, the point I'm making here is the state of the input can have an impact on the running time of your algorithm. Okay? On average, so I just said there's a best and worst case scenario. And let's generalize this. I said a bajillion. Let's generalize this and say you have some list of length n, where n is any arbitrary number. Usually we're thinking arbitrarily large numbers. Like it's a big number, but we just call it n. So the best case scenario is I look at one thing. The worst case scenario is I look at n things, right? What would you say the average case is? On average, given any two arbitrary, sufficiently random input, on average, where would the thing be in that list? How many things would I have to look at on average? About half of the things, right? Because for every time it's at the beginning, it's at the end. For every time it's at the second index, it's at the second last index, right? Like on average, it's going to be somewhere in the middle, right? So we can rationalize about our code like that anyways. But, no, we'll hit pause on that. So any questions about what I was just saying there? No, we're all good? We're all happy? So, all right, what do I have? Having correct code is clearly important, but we also want to make sure we have a good algorithm. Right, okay. So, if you come to me and you say, okay, I have a working solution and I've tested it. Good. And you're like, I've tested it and I know it's correct. And I look at your algorithm and I say, you're right. Your algorithm is correct. It's well written, like it's nice, good, clean code. It's correct, and it's tested, and it's clearly always giving you the correct answer, given the input. There's another dimension we care about, though. It's How good is your algorithm? And we've never really talked about what that means yet. Who wants to take a moment and think to yourself, and raise your hand if you have an idea, what would make an algorithm better than your neighbor's? What would you say? Using less memory, that's a good one. If you have code that needs a lot of memory, and the person next to you can write an algorithm to solve the exact same problem and it uses less memory, it's probably a good thing. What else? I'm asking a brainstorm here. What do you say? Easier to read. That's a big one. But that would not be in the dimension I'm interested in. You're absolutely right. But in the dimension I'm in, I mean, like, well, what makes an algorithm good? Readability absolutely is important, right? But yeah. Less runtime in the context of whatever that means. But yeah, like if you can run your code and it takes half the time theirs does, that's a good thing, probably. What else? What else makes good code? I like the good-looking code's good, less memory, less runtime. Any other ideas? Just probably less resources in general. It's probably a good one. Yeah.
Using doc strings and stuff so that a non-programmer can read the code.
I'd put that along with good code. Yeah, that's another good metric too, right? You really want that. But in terms of when I say, if I told you to do a linear search, and by looking at your code, I conclude that the person next to you wrote code that is linear. As I double the input size, the amount of work that needs to happen also doubles. But if yours is such that if you double the input size and the amount of work you need to do quadruples, that's bad code. Maybe bad's not the right word. It's certainly not efficient. It's not as good as one that takes less time. Maybe bad's not the right word, but there's a problem there. If the amount of time your code takes is quadratic, a fancy way of saying grows at a rate of n squared, where the amount of work that needs to happen relative to the input size is squared, and the person next to you is linear, it's just n. The squared one, terrible. You should feel terrible about yourself. You made a huge mistake. And I'm being silly, of course, right? I'm being a little silly. But, you know, in the context of today, it's important to have good code that, you know, doesn't take as much resources because resources cost money. And what do I mean by resources? I mean, like, yeah, compute time. How much work does your algorithm do? How much memory does your algorithm take up? How many processors does your algorithm need? These are all resources. And you're right. You know, if I hit run and your algorithm takes 1 second and the person next to you takes 10 seconds, whatever, right? But if you're like Google and you need to run that algorithm a bajillion times a day, yeah, 10 seconds is going to add up. Not to mention the electricity bill. Who here knows what the electricity are, what most of our electricity is in Nova Scotia? Like the type. It's true? Hydro? I don't think that's right. It's coal. I think most of what we got is like coal, right? So every time, I love when people get their electric cars and they're so happy. I'm like, great, yours runs on coal. Good for you. Obviously, it's better in the long run, right? I'm just being silly. But every time, if your algorithm takes longer to run, you're burning more coal. That sucks. So there are considerations here. So let's bring it back down to earth for a moment. I think this activity, I actually kind of spoiled it for you. Yeah, okay. Now, what if I told you, what's next here? What do I have? Complexity analysis. Okay. Okay, yeah, here we go. So the above highlights a huge idea of goodness with respect to algorithms. And at this, look, if at this stage of the game, if on an assignment you did a quadratic algorithm when you could have done a linear algorithm, you're not going to lose any marks or anything, right? Like, that's not what I'm trying to say right now. I'm just saying this is going to be something we're going to start to be aware of. And this is going to be something that we're going to become more aware of as we learn more computer science. So this is going to be a big idea next semester and subsequent semesters, right? That's all I'm really saying. This is where we talk about computational complexity. That's the word I'm using for really specifically talking about the amount of like computing resources that our algorithm needs. All right, so the main focus is usually time complexity at this stage, where that's like the run times, right, which is what you were getting at. But there's also like space complexity and processor complexity. There's other things there. But at this stage, we're often really worried about time complexity. And usually these things have big trade-offs. Usually these things have, well, I can have an algorithm that has a really good time complexity, but not great space complexity. Or I can have one that's really good space complexity, not as good run times. It's kind of where like dictionaries come in. Dictionaries like waste space, but man, they give you good run times. But these are trade-offs. There's no silver bullet. And if you can find a silver bullet, good for your particular problem. That's awesome. But usually this comes with trade-offs. So time complexity is the number of basic operations the algorithm needs to do, like units of work. It's a fairly abstract idea. And space complexity is the amount of memory algorithms require. To keep things simple, it's common to think about worst case scenarios, right? There's always a best case, average case, worst case. But usually computer scientists at this stage, when we're talking and learning about this stuff, we're really more focused on the worst case scenario. So we like to consider the amount of work required based on the size of the input. This is basically what I said moments ago. For example, worst case scenario for a linear search, haystack has length 10, the loop might need to run 10 times. Haystack has length 100, it needs to run 100 times. 10 million, 10 million, n, right? This is linear. As for space complexity, the linear search only is also linear. The amount of space it needs is, well, the space that the list takes up, how big haystack is. Assuming haystack has length n, then we require n amount of space. But if I told you, pick a number, let's have a very quick, what time is it? Do we have enough time? We have time for this. If I said, someone in the room, I need a volunteer. We're not actually going to do it right now, but I just need a volunteer. Okay. Pick a number between 0 and 1023. Okay, you got it? Now, everybody, if I start guessing like this, okay, is it 0? Is it 1? Is it 2? Is it 3? 4? 5? 6? 7? Are you for real? Let's pretend it wasn't. 7? 8? 9? 10? How many things am I going to have to guess to guarantee I find it? About 10, well, actually 1,024 because we started with 0, right? So there's actually 1,024 different things I could guess in order for me to guarantee that I found it. But what if I told you I can actually get it in 10 guesses or less? I promise you I can. Does that sound like a pretty good deal? I think it's a pretty good deal. If I say 1,024 guesses or 10, what's better? 10. But there is a catch. You have to give me one thing. I'm allowed to say higher or lower. Will you give me that? Will you give me that? Yeah? So get another number in your head. Don't make it 7. All right? Now, because I can't do arithmetic quickly in my head, I'm going to use a calculator here real quick. All right? So the number is, I'm going to guess 511. Higher. That's one guess. Someone who's going to keep track of my guesses? Okay, 1. Okay? 767. 2. 895. 959. 991. 1007. 999. I got it. And how many guesses? Okay. Say, that's magic. That was not intentional. And I would have got it if it wasn't, let's pretend it was like 998, just for the fun of it, right? Let's pretend it wasn't 999. So you would say lower. My next guess would be 995. 997? 998. And that would have been the 10 guesses, right? So worst case scenario was 10 guesses, but I kind of cheated, right? I was able to ask higher or lower. But then again, I could have asked higher or lower at the linear search, right? Was it 0? No. Is it higher or higher? Higher. Okay. Is it 1? Higher? Oh, okay. No, but what did I didn't go by ones. What did I do? Yeah, I always pick the middle. Let's say your guess was 0. My first guess would be 511. Well, let's say it was 512. Let's say your guess was 1. It's easier to do 1 in 1024, I think. So my first guess would be 512. You'd say lower. Then I would guess half of that, 256. Then 128. Then 64, 32, 16, 8, 4, 2, 1. That's how I would have done it. I'm always going halfway in between. And that was the guess. But what must be the case? The data that I was searching through, we're not going to have time for this. But let me put it this way. What I just did shouldn't have blown anyone's mind. If I said, open your textbooks to page 407, when you open your book, where do you open? Do you open the first page? And if it's not what you're looking for, do you just flip the page and go, well, that's not 500 either? Or what did I say? Open to page 407. Is page 1 407? No. Is page 2 407? Is that how you turn to that page in your book? No. You first probably go like, yeah, it's probably about here. And if you turn to page 500, right? So you turn to page 500. All the pages over here are less than 500. All the pages over here are greater than 500. And you're looking for 407. And let's say your book is 1,000 pages big. What side should you look at? You're looking for 400. These are all the pages less than 500. Here's all the pages greater than 500. You should probably look over here. How many pages did you just eliminate from your search? Half of them. Every decision you make, I eliminated half of the remaining pages. When I go 0, 1, 2, I only eliminated 1 page at a time. We'll pick up here Friday.